Okay, so who's got a joke? We're going to be talking about penile erection. So it's like there's like 1,000 jokes about that. Or phallus size. Come on, who's got one? Uh-oh. That mean you don't or you do? It doesn't have to, it's got to be about sex. No one? Really? Come on. You're disappointing us all. Okay. Here's a joke that's at least 500 years old. Okay. Only I heard it first in the Ozarks. Okay. But it's been traced back that long, which is a young man's interested in marrying a woman, and he takes her on a wagon ride, this the Ozarks, and he asks her if she knows, I don't remember the term exactly, but does she know what a penis looks like? She says, nah, never mind. See, this is why you don't want me to do it, to tell the joke. No one? No, I already messed it up. You have a joke? Or are you going to finish my joke? Yeah, okay, all right, hold
on. So what's the difference between a tire and 365 used condoms?
The difference between a tire and
365 used condoms.
365 used condoms.
Yeah, one is a good year, the other is a great year.
Yeah. Okay. And there's a whole slew of those sorts of jokes. Like, what's the difference? I mean, the difference between a long distance runner and a woman in a bathtub. The long distance runner is a pant in the country. Okay, on. So we've been talking about male reproductive anatomy, urogenital system. And the last thing we were pointing out was that in semen's the word for what comes out in ejaculation, and sperm is a tiny proportion of that. Most of it's coming from the seminal vesicles, most of the semen, and some from the prostate. And we know quite a bit about the biochemistry of that process. So when the sperm are leaving the where are they leaving? They're leaving, they're going through the vas deferens, and they're on the way to the base of the penis. Where are they coming from? Epididymis, thank you. When they leave, they are not, the term is capacitated. They're not able to fertilize anybody. But in getting mixed with fluid from the seminal vesicles and from the prostate, they get exposed to this gemisch, I think that's the technical term, of several molecules, including one called seminal and from the seminal vesicles, and from the prostate-specific antigen, PSA. And put together, they will prepare the sperm as they're in the semen to fertilize. So there's zinc, there's got to be zinc around, and the zinc triggers the formation of the gel, but the PSA snips up the seminogelin, and in the process, the sperm get capacitated. And so now they become active. They've been pushed from the epididymis to the base of the penis through the smooth muscle in the vas deferens, but now they've become capacitated. They start wiggling around and they start looking for a target. And so, and this is one of the reasons why all these fluids are coming in there. You might think, well, why not just deliver the sperm? I don't know the real answer to that, But it appears that natural selection has decided that the sperm stay more stable in the epididymis if they are not capacitated, and then it's arranged for the right mix of chemicals to happen only at the point of ejaculation, and now they're ready to reproduce. And questions about that? So yeah, I do want you to know that. Yeah. Oh, prostate-specific antigen. And as men get older and their prostates get bigger, their levels of prostate-specific antigen that you can discover in blood goes up too. And so there was great hope at one time that this would be a great marker for prostate cancer, not benign prostate hypertrophy, but prostate cancer, because some prostate cancers really shoot up PSA levels. And so right now it's recommended men past a certain age get their PSA levels measured every year just to keep track of that. But it's possible that this test has done more harm than good because it's not very specific. There's a lot of false positives. Sometimes PSA levels go up just because they go up and there's no cancer there, et cetera. Okay. And the other thing that you may have heard about, and that I want to point out, and I was talking to Premica on the way here, that with all this stuff, you know, all the, misinformation coming out of Health and Human Services, about I can't believe we're once again talking about vaccines and autism. We'll get there just a moment, but I can tell you, I mean, cases of autism have risen. Partly that's because it's diagnosed more often. The diagnoses have changed. But I think most people think it really has risen. But one of the things we know for certain cannot be responsible for it are vaccines. And the idea got started when this British doctor made up the data because he had a service that was going to make him a fortune. And it did, but the data were made up. There was never a link. Tylenol and autism, who knows, right? I don't think anybody knows. I can tell you, no, I've got to stay away from that. Oh, I had a point. Oh, well, it'll come to me eventually. But there are certain trends that are clear. Worldwide data, we'll talk about later, the fact that girls are reaching girls are reaching their first period at earlier and early ages, and that's been happening since the beginning of the 20th century. Every country that's tracked, it's a thing. And nobody knows what's the cause of it. And another thing that's quite clearly happening all over the world is a decline in the number of active sperm in semen samples from men from around the world. And no one understands why that's happening. But for both cases, you know, there are concerns that the same sorts of things, that it might be some environmental factor, such as various chemicals, because the rise of the 20th century, that rise in the 20th century, is also a time when chemical industries became worldwide, and it suddenly became really profitable to make pesticides and fertilizers and stuff like that. So is that responsible? We'll talk about age of menarche, the beginning of the period, in a little more detail later. But in terms of sperm count, I think it's safe to say that no one understands what might be behind it, and there are a host of possibilities. Yes, yeah.
But the Y chromosome is also slowly getting like smaller and smaller and subsequent.
It's a great question. We'll get to it in chapter 4, I promise. And evolutionarily, Y chromosomes are getting smaller because really, they're just wimpy little chromosomes. That's chapter 4. Okay. So I've included these tables, not that you need to memorize them. Believe me, this is not an exhaustive table of all the hormones that are known, or well understood, not even the table of all the hormones that are known to be important for sex and reproduction, right? It's a very selective list. And I show it because I do want you to know this material, because these are all hormones we either have talked about or are going to talk about. And you might impress yourself with, certainly for these two, you might impress yourself with how much of this table you already know. I mean, test yourself on it by all means, but we've already covered most of these things. Maybe the exception is we haven't talked about these hormones very much, and we'll get there, but it's coming. So don't panic when you don't understand the role, what these hormones in the third part of this table, what that's about. Okay? But I wanted you to have it for a reference. I've mentioned this a couple of times, that in biological systems, the release of hormones is never steady. It's never a constant level of hormone X, Y, or Z. That's just not how biological systems work. Because of biological rhythms, some of which are shorter than a day, many of which take about a day, so-called circadian rhythms, for the most part, hormones are released in complicated patterns. And we didn't really know that right away. It took the time, it took the innovations of having really sensitive blood assays and someone going to the trouble of taking samples every 10 minutes, right, to see what things are like. But it turns out that when you do that sort of thing, this is an absolutely typical pattern where in most men, the peak of their testosterone is in the morning, and the nadir or low part of their testosterone levels are in the evening. And even in the course of a day, there is this so-called ultradian rhythm, you don't need to know that, where there are these peaks and valleys. And when people study this in systems, it's clear that the same amount of hormone released constantly will not have the same effect as an amount of hormone that is released in a peak and a valley. For growth hormone, you don't have to remember this, I'm just giving an example. For example, growth hormone, the way to get a lot of growth from growth hormone isn't to have a constant level of it, but rather take that same amount of growth hormone and give it in peaks and valleys, deliberately infuse it in peaks and valleys, and it's much more effective. So it's clear that these changes over time, these fluctuations, are biologically important. And it's the sort of thing that you just cannot mimic by going to the drugstore and taking something. And so anytime people are having hormone replacement therapy, we are handicapped by the fact that we're simply trying to guess what constant dose, or more or less constant dose, would be equivalent to in life. Again.
That, you know,
Yeah. No. And so if you're taking exogenous testosterone, there are various amounts. If you're taking it, there are tricks you can use, ways you can conjugate testosterone so it doesn't all go into the bloodstream at once. So when people are taking testosterone, it's virtually never just naked testosterone by itself, because the problem with that is there'll be a very high peak and then there'll be a crash. So if it's taken orally, the testosterone is chemically modified so that it won't dissolve, won't go into circulation until that additional ester that was added to it, propionate, gluconate, something, it could be anything, until that lets go. And then the testosterone is free to go into the bloodstream. Other ways of treating are with skin patches. And what's great about those is those gels have been designed to really have a very constant release of hormone. In no case does anyone know how to provide anyone with a level, a pattern of testosterone levels that are like happens in nature. Ian?
With exogenous testosterone, how rapidly does it, does like the negative feedback loop kick in and lower your?
Another great question, given what I was talking about before, the only testosterone that matters is once it gets into circulation, comes out of the depot and into circulation, and it's it as soon as it's in circulation, it starts having an effect. It takes a while for the negative feedback to affect GnRH release and to affect gonadotropin release, but it absolutely happens. Yeah.
A certain amount of testosterone at certain throughout the day.
One could design, I'm sure, a device. It's got to have a motor in it. It's got to have a timing device in it. It's got to have access to your bloodstream 24 hours. And indeed, one of the great innovations in medical science for people with type 1 diabetes is the construction of these devices that are both monitoring glucose levels and deciding about letting insulin out. To my knowledge, no one's tried to do that with any gonadal steroid treatment. Why? It's expensive, right? I mean, the insurance companies can justify making such an expensive device, to keep someone alive. And it used to be type 1 diabetes. That meant you were not going to live to old age, even with insulin injections. And that's totally changed, partly because of better understanding of how to dose, but also partly because of these machines that are letting people live longer and longer. So one could do it. I don't see anyone, it would be so expensive, I don't see anyone doing it. And clearly, exogenous hormones, they work, right? So it's good enough. And yeah. And in general, steroid hormones like that, they're incredibly stable. They don't break down very easily. So as biological treatments go, not bad. Okay. I'm now going to talk about Appendix B, where I'm going to explain Neuroscience 301 in 5 minutes. And for those of you that already had 301, you don't care. But for those of you who haven't, so try to catch me that I'm saying something wrong and correct me. And for those of you who don't know it, this is going to go fast, but it's there in the appendix and you can catch up. So every neuron is an information gathering, information processing machine. It has a cell body, as all cells do, that keep it alive and metabolizing and things like that. And it has inputs on extensions of the cell. They're known as dendrites, where there are connections called synapses, where another neuron gives this neuron a message. And the job of this neuron, this little information processing machine, is to gather up all the information from thousands, sometimes tens of thousands of different synapses that might come from many different neurons and many different sources of neurons, and eventually to make a single decision, either to send an electrical signal down the axon or not. And once it makes that decision, the electrical signal, called an action potential, is always the same. And so this information processing unit is taking in information in all of its dendrites, and it's making a decision about whether to have an action potential or how many action potentials to make. And the reason your brain is able to solve almost any problem is because when you put trillions of little information processing systems like this together in a proper way, you can pretty much solve anything. So Inside each synapse, there's a presynaptic cell that is going to release little packets of a chemical into the synapse to stimulate the postsynaptic cell. And we call those chemicals neurotransmitters. The chemicals are packaged in little vesicles, and different neurons release different neurotransmitters. Some neurons release more than one neurotransmitter, and some neurons change which neurotransmitter they're using, especially during development. And this means that each postsynaptic cell, the dendrite, has to be able to respond to whatever neurotransmitter is hitting it. And the ways that postsynaptic neuron controls that takes another whole course. And I'm not going to give that to you in 3 minutes. Okay? And in terms of sex and sexual response and sexual reflexes, we have to understand how neurons like this communicate with each other in order to affect behavior. And in the spinal cord, we're going to spend quite a bit of our time in a moment. In the spinal cord, there is the part of the spinal cord towards the back that's called the dorsal, and the part of the spinal cord that's toward the belly that's called the ventral. And we are so lucky that somewhere in the evolution of vertebrates, a decision got made by natural selection. Well, it wasn't a decision. Natural selection hit on a mechanism, whereas all the sensory information is coming into the dorsal part of the spinal cord, and all the motor commands are coming out of the bottom part of the spinal cord. And so we talk about sensory input to the dorsal horn through dorsal roots, and motor commands going out to the ventral horn through motor neurons. Because among other things, they control muscles, also glands, other things, but we can lump them together as motor neurons. In between, there are lots of neurons that take the sensory information, integrate it, put it together, and pass it on to the motor neurons. Where do these neurons live? Well, for everything we're going to be talking about, the sensory neurons in the spinal cord, the cell bodies are in these lumps in the dorsal root that's called a dorsal root ganglion. That clump of neurons, it's called a ganglion because it's outside the central nervous system. And that's why we're calling it a ganglion and not a nucleus. We'll come back to nuclei in a moment. And the neurons that are sending out the motor commands, they live in the spinal cord, in the ventral portion of the spinal cord. So their axons don't have to go very far to go out the ventral root and cause things to happen. This happenstance was that sensory information comes in the dorsal root and goes out the ventral root. It's so obvious that 18th century scientists understood it. Right? So that makes things easy for us. Within the spinal cord, all the cell bodies are clumped together in the middle. And some of these cell bodies are sending their axons up and down the spinal cord. And so these interneurons, many of them, send their axons out to what's known as the white matter to either go up to tell something to the brain or down to talk to other spinal segments. And also the brain is constantly talking to the spinal cord. So much of this outer part of the spinal cord consists of axons that are sending commands from the brain to the spinal cord. You'll see there that the center of the spinal cord, the butterfly-shaped thing, is called gray matter because it consists primarily of cell bodies and synapses. It's packed to the gill with neuronal cell bodies and synapses, dendrites, and all that stuff. The outer part is called the white matter because those axons, in order to move really fast, are coated with a fatty material called myelin. And fat, as you know, think of Crisco, is white. And so when you look at a spinal cord, the reason the outside looks glistening and white is because it's full of fat. And the reason the inside the spinal cord looks gray is because there's almost no fat there. It's lean. It's full of proteins and structures and stuff like that. Doing so far, so okay. And I guess the brief discussion of the brain, the parts that we care about are really the bottom of the brain. Almost everything about basic bodily functions is controlled by a part of the brain called the hypothalamus. Sometimes it's considered part of the brain stem, and sometimes it's not. I don't care. That's not important. But it is full of different clumps of neurons called nuclei, and many nuclei there, clumps of neurons, are involved in more than one function. Name a bodily function, and the hypothalamus is important to it. Body temperature, heart rate, respiratory rate, glucose utilization. There is nothing that your body's doing that I know of that the hypothalamus doesn't have a say in it. And all you're in charge of are other parts, right? Because the other interesting thing about the hypothalamus is you have virtually no voluntary control of any of the processes that are going on. So this is the automatic control center of your brain without which you'll die. You'd be dead already. And you can think of the rest of the brain as an important organ for gathering information and sending instructions to the hypothalamus. Do this, do that. And the rest of the brain is important for you to do things that you have voluntary control over. This part of the brain that is continuous with the spinal cord is known as the brainstem. And the parts we'll be talking about the most are the hypothalamus and this part, this fat part, that's called the pons because it's a bridge. It's full of fibers that are crossing the midline there. And the medulla that is immediately contiguous to the spinal cord. We won't be talking about the cerebellum much, but it's important. It used to be said that it was important for motor control, and it is, but it's important for almost everything, including higher cognition, things like that. Almost there. And so here's a sensory network at work where the neuron lives in the dorsal root ganglia, or DRG. It has a single process, and you can consider it one long axon, but at one end, it branches out into the body and gathers information. Touch, pain, stuff like that. And the action potentials in this kind of a neuron start there and then work their way into the spinal cord and bring information to neurons in the dorsal horn, for the most part. Questions about any of that? So there are lots of different sensory neurons that have lots of different specialized endings out in your body to gather particular information. Some of those branches have very clever little machines that trigger an action potential when temperature changes quickly. Others have very clever machines embedded in the membrane that detect when damage has been done. Others detect when something brushed the skin lightly. Still others when something pushed against the skin, and loads that detect something you might not have expected, which is whenever there's a vibration in the skin. Why would nature need you to pay attention to vibration in your skin? Yeah. I don't think earthquakes were common enough it's totally not intuitive. The time you need for your skin to detect vibrations is when you're taking your hand and rubbing it over a surface. That's how you detect texture. How many people, you've taken 301 and 302 and nobody explained that to you yet. Okay. Huh? It makes me happy. I won't tell your instructor. Okay. And we've only recently known that they're in genitalia, specifically in the glans clitoris and the glans penis. There's a kind of sensory detector that is found nowhere else. And it looks incredibly complicated. And basically, it is extremely sensitive to touch. And when the glans is engorged, it becomes more sensitive to touch. And so these are the parts of the body. These are specialized structures that make genitalia really, really sensitive to touch. And they're called genital involves. How are you doing with that? And there are lots of other touch receptors, but I'm not going to talk about them. Yeah. Uh-huh. Right. These neurons with the cell bodies in the dorsal root ganglion, they have this process that goes out, call it a dendrite or axon, I don't care, but the whole thing can send an action potential. And at one end, often the axon just breaks into really fine branches. And for years, we called those free nerve endings, and no one had any idea how they detect anything, right? But it turns out in those cases, within the membranes of those axons, there are proteins that are specialized to detect pain or cold temperatures or high temperatures, where they're such that when that happens in that area of the skin, they'll send an action potential. Is that? And then it will synapse at this end, it'll synapse on neurons in the dorsal horn that will send the information on or not. Did I get it? Okay. So far, so good. Next, I'm going to talk about sexual arousal in men. This is chapter 3. And to do that, I have to tell you something more about the nervous system, which is we call that part of the nervous system that's the brain and spinal cord is the central nervous system, or CNS. And the rest of the nervous system, all the neurons that live outside your body, they're all part of the peripheral nervous system, or the PNS. And for our purposes, there are two systems that we've known about, again, since the late 1800s, that are important for sexual arousal and erection in both men and women. To understand that, we have to talk about, it's known as the autonomic nervous system, because again, it's a part of your nervous system you have no voluntary control over. And the autonomic nervous system has traditionally been divided into two main parts. One part was understood earlier because it's so prominent. If you dissect a vertebrate, the spinal cord is inside a very bony, hard to get at case, a series of discs, vertebrae, that make it protected. But right next to the spinal cord, lying outside that vertebral column, is a whole line of ganglia, clumps of neurons. And there's one on the left and one on the right. And then on the ventral surface next to the vertebral column. And so they're protected that way. And because they make a chain of lumps, it's known as a sympathetic chain. And these are sympathetic ganglia. We won't talk about why they got that name in the first place. It's historically interesting, but not relevant. But in general, the sympathetic nervous system is intended to activate the body, to make the body ready for action. So it's sometimes known as the fight or flight system. And it's a complicated system because the decision about whether to activate the sympathetic nervous system, first of all, it starts in the brain, and the brain communicates to the spinal cord. And so the first neuron in the relay that activates the sympathetic nervous system actually resides in the spinal cord. And it's going to send its axon out and synapse within one of the ganglia there. Synapse on a neuron there. And that neuron in turn is going to send out its axon to some part of the body. Some axons go to the heart, and if the sympathetic nervous system is active, it will command the heart to increase heart rate. And if it's going to the, no, I don't want to say it. And if it's going to respiratory centers, it will activate and increase heart rate. It will cause the pupil in the eye to get bigger, to dilate, in order to be more sensitive to visual information, etc. How's that? The brain decides, sends command to the spinal cord, spinal neurons send their axons to the sympathetic chain, and sympathetic neurons in the chain send their axons to the target organ. We call this neuron that's before the ganglion the preganglionic neuron, and the neuron within the ganglion is a postganglionic neuron, because this is the direction of information flow. There's a great mnemonic that is available to explain which parts of the autonomic nervous system are important for sex. And the sympathetic nervous system, the mnemonic is S for sympathetic and S for shoot, because it's going to be important for ejaculation. The other part of the autonomic nervous system is organized differently, and the part we care about is the part that's at the bottom of the spinal cord, where the preganglionic neurons live in the spinal cord and send their axons out not to the sympathetic chain, but to ganglia that are found near every organ. There's a clump of neurons, a ganglion near the heart, another near the prostate, another near whatever organs you've got. All of them get stimulation by both the sympathetic and parasympathetic nervous system. And so the ganglion is nearby, and then the postganglionic neuron sends an axon to, in general, prepare for rest and relaxation. It is one that's going to reduce the activity of the body and therefore reduce its ability to react. But it's, sometimes known as the, rest and relax, which is not a bad idea. How is it that the sympathetic nervous system and the parasympathetic nervous system have opposite effects on the heart, the eye, etc.? It's because the postganglionic cells release different transmitters. In general, sympathetic postganglionic neurons release norepinephrine, also known as noradrenaline, and like adrenaline that you know about, it excites things for the most part. The parasympathetic nervous system, in that case, the postganglionic cells don't release norepinephrine, they release a different neurotransmitter called acetylcholine. So norepinephrine will cause the heart release, and the heart will cause it to speed up, and acetylcholine will cause it to slow down. And in fact, your heart's constantly getting both kinds of stimulation, and your heart rate is a result of the function of this brake and accelerator. How's that? So what's the other part of the mnemonic? In erection, it's the parasympathetic nervous system that's important for erection. So point and shoot. Parasympathetic nervous system for the erection to happen, sympathetic nervous system for the ejaculation to happen. And we won't talk about how that's been demonstrated, but it's quite clear. How are you doing? Okay, one more. The autonomic nervous system, like every part of your body, is controlled by the brain. So the brain is constantly sending axons down to the spinal cord to modulate the preganglionic neurons that reside in the spinal cord and to decide what these two systems are going to be doing at any one time. And here's just a little more detail telling you what I did already. So the penis will get more erect in men who have no connection between their brain and their spinal cord, where they have no sensation from the penis. In some cases, at least, physically stimulating the penis will cause it to become erect. So we know that's a spinal reflex, where stimulation of the penis activates which nervous system to cause erection? The pointing nervous system, right? The parasympathetic nervous system. And in so doing, by the way, there's a positive feedback loop there because as erection continues, all those sensory endings become more sensitive. They're easier to stimulate. Maya? Yeah. Sorry. Yes. And at some point, again, in some men where there's no connection between the brain and the spinal cord, and at least some men, it can, stimulation can eventually cause the system to ejaculate, so that the man's body will ejaculate. And that happens when the sympathetic nervous system takes over and triggers that change. How are you doing with that so far? Okay. And all these details, etc., I'm going to simplify it for you. All of these things happening in intact individuals in the spinal cord, these spinal reflexes that can happen without brain input, but normally they're being inundated with brain input. So the brain is constantly modulating spinal reflexes to decide when they'll happen or if they'll happen at all. The brain has total control over whether these things will happen. So one of the other things that happens is, of course, in someone with an attacked nervous system, not any old stimulation will cause an erection, right? Because the brain is making a decision about whether, in fact, the person wants to have an erection. Unless you're a teenage boy, then it, it sometimes thinks on its own. But in the normal course of events, it'll be the brain to decide whether this is a good time for stimulation of the penis to result in an erection. If, for example, the person is stressed, that isn't going to happen. And the stimulation of the penis may be the same, but the erection's not coming because the brain's going to override that. And likewise, if the person's brain has decided this is a great partner, a great time, etc., then the erection's more likely to happen. And I've already told you the erectile portion of the part of the penis that is responsible for the stiffness of erection are those two cigar-shaped chambers on either side of the shaft of the penis known as the corpora cavernosa. And so parasympathetic stimulation will cause them to expand. They also cause an expansion in the erectile tissue of the corpus spongiosum, but it's not responsible for the stiffness that happens. And with enough stimulation of the penis or enough encouragement from the brain, even if there hasn't been that much stimulation of the penis, then the brain will have the spinal circuits trigger ejaculation, and that's when the sympathetic nervous system gets activated. Yeah, well, thank you. Ian, yeah. No, both systems are there, and there's no, we'll talk later about female ejaculation, a controversial topic, but it's not the machinery for ejaculation is primarily the important parts are the seminal vesicles and the prostate, et cetera, and the vas deferens. But another contributor are the striated muscles of the pelvic gland, that pelvic region, and those tend to stimulate rhythmically, as we'll see, and that's true in both males and females, and that's the sympathetic contribution to women. All right. So let's talk some more about those parts of the penis that are important for erection. So this is a cross section of the penis. Here on the ventral surface, the undersurface, is the corpus spongiosum with the urethra going in the middle of it. And on either side of that, on the dorsal portion of the penis, the part that if the penis is erect and sticking out is pointing towards the head, are the two corpora cavernosa. And you see inside, for the most part, the corpora cavernosa, all these erectile tissues, are mostly full of collapsible cavities that are known as sinusoids. So sinus just being anatomical word for an opening, a hollow place. And when there's not much blood in those sinusoids, this whole structure doesn't take up much room. And so it's small. In order for erection to take place, these sinusoids have to start trapping blood and filling up with blood. And because corpus spongiosum, corpus cavernosa are surrounded by very tough, fibrous outer covering, there's an upper limit to how much blood it can take, but also there's going to be a stiffness happening as those sinusoids fill up.
What are we talking about?
A great question. I have no idea. Yeah, if you happen to have a penis, you can measure it yourself by asking how much water is displaced when it's flaccid and how much is displaced when it's erect. And I'll bet somebody's done that, and I have no idea what they found. And yeah, I know. Just think of all the things I could have said there, but yeah, so it's knowable. I don't know. And as long as we're talking about jokes, I'm gonna show you something you're never gonna be able to unsee. All right, this is perhaps one of the grossest images in the course, so be prepared. Which is that the appearance, yeah, it's you're never going to be able to see ski goggles again without thinking about this. Okay. So here's more detail about how the penis becomes erect. It's also true of the erectile tissue in the clitoris, of course. But as we're going to see, there are, for whatever reason, no, you already know why. Concerns about how penises become erect have for some reason gotten a lot more attention from the medical field than how clitorises become erect. Gosh, I wonder why. So here's the way to understand what's happening here is with the blood vessels, two different things are going on. Sometimes some blood vessels, the arteries, are being constricted and the veins are large, or the other way around, where the arteries are large and the veins are constricting. But the way to understand, well, where do I have that? Parasympathetic activity that is responsible for pointing, et cetera, is that the parasympathetic nervous system opens up the arterial flow to those sinusoids. And so this is a cartoon sinusoid. So imagine there's thousands of them, certainly hundreds, I suppose thousands of them inside each corpus cavernosum. And so another thing that's going on is that each one of those sinusoids is surrounded by a tube of muscle. So what's happening is that that trabecular smooth muscle, you don't need to remember trabecular, just smooth muscle, it's relaxed. And the arteries are opened up. And once that starts happening, once the sinusoids start filling up, it automatically closes the arterial, pardon me, yeah, the venous outflow. And so those veins outside the sinusoid get pushed together, and now there's more blood coming into the penis than going out, and it's, conservation of volume means the penis is going to get bigger. How you doing so far? For this to happen, the sympathetic nervous system has to be inactive, because one of the things the sympathetic nervous system does is increase your blood pressure. And one of the ways it does that is by making the blood vessels smaller, the arteries smaller, to boost blood pressure. Why? To push more blood out into muscles and places like that where you might need it if you're about to fight for your life. So the sympathetic nervous system has to be quiet, and the parasympathetic nervous system has to be working, has to be relaxing those muscles so the sinusoid can get bigger, and that will collapse the veins so that the blood can't get out. An erection happens. Then to go back, when the penis is flaccid, the sympathetic nervous system is more active, and it's closing off the arterial inflow to the penis, to the corpus cavernosum, to the sinusoids. And also, the smooth muscle is being contracted. And so it's keeping the sinusoid from getting bigger. And there's not much inflow. And in keeping the sinusoids relatively small, the venous blood is perfectly open and relaxed, and it's easy for blood to go out. So controlling erection of the penis is simply a matter of controlling both the inflow and the outflow and those smooth muscles around each sinusoid. How's that? So understanding this means you can understand drugs that help with erection. So it turns out that the parasympathetic nervous systems that are releasing acetylcholine, they also release a transmitter that's called nitric oxide, not nitrous oxide, nitric oxide. And it is important for this process to be happening, the parasympathetic nervous system. And Viagra works. Whoops. Oh, yeah. And what the nitric oxide does is it increases levels of another compound called cyclic GMP in the smooth muscle walls. And so the walls relax, and so no erection is happening. It turns out Viagra short circuits this step, because what it's doing is it's inhibiting an enzyme that normally breaks down cyclic GMP. Oh, so now the cyclic GMP sticks around longer, right? Because the enzyme's being handicapped. And that means there's going to be more cyclic GMP in those muscle walls. They're going to relax and let the sinusoids fill up, which, remember, will automatically collapse the venous outflow. So there's lots of these phosphodiesterase 5 inhibitors. That's the name of the enzyme. And yeah, question about that. Yeah.
that because this same mechanism of process occurs in like other things?
The phosphodiesterase is working throughout the circulatory system. So yeah, that can be a concern. And I don't want to go into the I don't know that I know the details, but yeah, certain conditions, it's really a bad idea to take it. But yeah, other questions like that. Okay, so I can't pass it up. There's got to be a few jokes. You've all been at a meal with this guy. I mean, even if he didn't get around to Viagra. Oh, and I think, did I include this in the slides? Yeah, so you can read there a really great op-ed. It was in the New York Times about now we're you know, never mind. You'll read it for yourself. Another joke. I'm convinced. You know how you'll hear cars that are really, really loud, and it's not that the muffler's broken, and it's not even that they're going that fast, but they're really, really loud. I'm convinced that every man who drives one of those really loud cars or a Hummer, I'm convinced they have really tiny penises. This is science. Next time you see such a person, tell them, ask them, you know, I hear that men who drive Hummers have really tiny penises. Is that true? And if they get mad or red in the face, what more proof could you have? Clearly. Okay. Oh, yeah. There is a great risk of these drugs, which is that sometimes the situations are such that in taking the drug, well, first of all, even without Viagra, it would sometimes happen that something goes awry with the erection mechanism, such that even after ejaculation, or in other cases where for whatever reason ejaculation never happens, where the erection is maintained for long periods of time. So sometimes that happens, and we don't know why, and that's known as idiopathic. Idiopathic means we have no understanding of how it happens. My joke is idio means we're idiots about this. We don't know a thing. And in medicine, there are lots of idiopathic cases, which makes it sound like they have an explanation for it. But what it really means is we have no explanation for this. But you got to admit, it sounds impressive. And that can be a medical emergency, because in order for the tissues in the erectile, in order for the cells in the erectile tissues to stay alive, they can only do without normal circulation for so long. And if the supply of oxygen, for example, and glucose, if it can be interrupted for a short while during erection, and they're fine. They're designed to handle that. But if it goes on for too long, they will die. And once they're dead, we have no way of bringing them back. And so it would sometimes have, this medical condition is known as Priapism because of a Roman god or demigod or something who, famously had really long-lasting and enormous, erections. So that's, you can see he has a foreskin, but poor thing, he has to have a crane system to hold on to it. Or here's another indication on this ancient coin where this guy, and so supposedly this was the nature of Priapus. I don't know that in these cases they understood it to be pathological or a problem. They were just celebrating, Roman guys will be guys. But in any case, and certainly taking Viagra and such erection-enhancing drugs, they certainly increase the chance of that. And if an erection lasts more than, than, did I put it up there? Than an hour or so, and especially if there's been an ejaculation, Yeah. There's been an ejaculation and still the erection isn't going away. That's when you go to the emergency room. You don't call the doctor and ask what you should do. You go to the emergency room where they see this all the time, and they can give you drugs. I actually don't know what they are, to counteract that. And if you don't, after a certain amount of time, there'll be necrosis in the penis, and the erectile function will be impaired forever. Yeah. I have no idea. I did not know that. So I guess the idea is if the brain is no longer acting on the spinal circuits, then the reflex has been triggered. I didn't know that. Makes sense. Yeah. What's the mechanism? All that's being controlled in the spinal cord, where it reaches the point where there's been enough stimulation that the ejaculation is going to be triggered. Of course, the brain has a say in that, as in all spinal reflexes. So it's also modulating the circuit and deciding, is it time? And when we talk about sexual disorders, there are, time. I mean, the biggest complaint that men have about sexual dysfunction is when they ejaculate sooner than they'd like. Well, no, the biggest complaint is they can't get an erection. The second most common complaint is um, is um, is that they ejaculate too soon before their partner's ready. Or yeah, pardon.
Psychological EDs, like where you
We'll talk about that in a moment. There's a great test that was available before Viagra existed. If a man isn't having an erection, to see whether there's something wrong with the machinery. And the test, it was incredibly sensitive. It was, when you wake up in the morning, do you have an erection? Because as we'll see in a little bit, during REM sleep, erections happen spontaneously, and most people, the last episode of the evening is REM sleep. So if the person says, I can't get an erection when I'm wanting to have sex, but when they wake up in the morning, they have an erection, then it's probably a psychological problem. Which doesn't mean that Viagra won't help, right? Because it just kind of ups the dial in terms of how easily they can get an erection. And, sometimes men as they get older, turns out they used to be interested in having sex at night, and now they're interested in having sex in the morning because that's when they can have an erection before Viagra. Can someone get an erection without being sexually attracted? Absolutely, yeah. And I guess we don't talk about this later, but anyone who has a penis, if you talk to, there was a stage in development at puberty where sometimes it would become erect with absolutely no understanding of why, and could be very socially inconvenient, right? I won't ask people to, but talk to someone who has a penis that trusts you enough and ask them. Unwanted erections can really be a problem, but eventually it goes away. So that's probably best understood as the spinal circuits are not mature enough in terms of the brain modulation. Oh, okay, you're agreeing with me. Okay, well, let's Kahoot. So, okay, plenty of time. So here's what we're going to be talking about next. Why was I talking so much about the fact that the brain sends axons down the spinal cord to control spinal reflexes? Because in the brain, there are both supraspinal influences that promote erection and ejaculation, and those that inhibit it. And the clearinghouse for all of those decisions is the hypothalamus. And another area that's involved is known as the locus ceruleus in the pons. And then there's another nucleus I want you to know about, the paragigantocellular nucleus. The name just means it's around the giant cells, right? And they send their axons down the spinal cord. And these paragigantocellular nucleus cells are there to inhibit erection. They inhibit erection by sending axons to the spinal cord, and there the axons release serotonin, a different neurotransmitter, neither norepinephrine nor acetylcholine, but serotonin. And serotonin acts on those spinal circuits to short circuit erection. And so they'll stop it. And this is relevant to sex because still the most prominent antidepressants are the selective serotonin reuptake inhibitors, so called because they inhibit the reuptake of serotonin from synapses. And in doing that, the serotonin sticks around longer in the synapse. And that means the serotonin will be stimulating the postsynaptic cell longer. So SSRIs are known to have an antidepressant effect in many people, including Prozac. And the mechanism by which SSRIs work is very well known, right? That is, that it's selectively inhibiting the reuptake of serotonin, presumably in circuits in the brain. You will hear people say that this shows that depression is a problem caused by not enough serotonin stimulation. Of all the things we know in neuroscience, we know this cannot possibly be true. Because when people take SSRIs, the effect on serotonin in synapses everywhere in the body happens within an hour or two. And yet, for the SSRIs to relieve depression, they have to be taken for weeks. Okay? So the depression is not relieved simply because the person didn't have enough serotonin in synapses anywhere. The depression is relieved because the brain compensates what the SSRI does, and somehow that compensation reduces depression in many people. You cannot leave here with a neuroscience major and think that depression has been shown to be due to not enough serotonin, because that we know for a fact isn't true. If that were true, then the first time you take the SSRI, the depression would be relieved, but it takes weeks. And there's nothing different about the activity of the drug between the first dose and the 14th dose. However, it's a two-edged sword, because when you take that first SSRI, it's also going to be inhibiting serotonin reuptake in the spinal cord. The drug goes everywhere. Wherever the bloodstream is, it's going to go there. We're doing fine. I hate that clock because it's fast. Don't look at that. Pay no attention to that clock. So for some people, there is sometimes an unwanted side effect of SSRIs, which is that it will make it more difficult for them to get an erection. And it turns out that when people are seeking treatment for depression, it sometimes happens that the first SSRI they try isn't effective. And so then they'll stop taking that SSRI and try another one. And clinicians have pretty good ideas about which ones work and what order to try, but it's something of a trial and error process to find the SSRI that is effective for that person. Sometimes they'll go to other antidepressants, like SNRIs and things like that. But my point is that just as some SSRIs relieve depression in some people and not in others, the same is true for this side effect of the SSRIs. An SSRI that causes a difficulty in getting erection in a particular person If they switch to a different SSRI, that problem sometimes goes away. So, so another part of the trial and error process is first finding an SSRI that's effective, and then if you have this side effect that you're unhappy with, maybe trying other SSRIs until you reach that sweet spot where the depression is being relieved, but erectile function continues. Why there are individual differences in the different SSRIs, in their effect on depression or their effect on erection, nobody understands. Nothing. We don't know anything about it. Because mechanically, in terms of the mechanism, they all do the same thing. But the formulations vary, and for some people, they have that effect. A particular one has that effect, and another one doesn't. Question about that? Yeah. You had asked me a question. I've got 3 minutes. I don't want to start another whole topic. Yeah, good, thank you. Pardon? Is there an effect on libido of SSRIs? It's difficult to untangle. For some people, yes, that's another possible side effect. And, one strategy is to try different ones to see if it returns. Of course, for men, it's hard to untangle how their libido is if they start having a difficulty getting erection, then worrying about whether they're going to get erection makes it difficult for them to have an erection, etc. So it's complicated, but it's not unusual for women to report a drop in libido with one SSRI that often goes away if they try another, or then go to a different class of antidepressant. Okay? Okay. When we get back, we'll talk about female sexual arousal.